Hi there, this is Ms. Page. In this lesson, which is the first lesson in Unit 10 on logarithmic functions, we are going to introduce the concept of a logarithm, what it is, how to write them, what they're related to as far as their connection to exponential functions, and also learn how to evaluate them. So, logarithms are basically the inverse of our exponential functions. So a logarithmic function and an exponential function would be inverse functions. And so know that when we have an exponential function shown here, our f of x equals 2 to the power of x. X, remember, is the exponent. And then the y value then is the value of the power 2 to the x. So if x is 1, then the y would be 2, the value of that whole power, 2 to the first power. So when we do the inverse, remember, what happens is that they switch. So that means that our x, which is the exponent in an exponential function, in a logarithmic function is going to become the value. And the value of the power actually becomes the exponent. These two will switch. And so that's the big idea here, is that when we talk about a logarithm, what we're really talking about is the value of an exponent. And that is the big key idea to help with making sure we understand and do many of these logarithm problems correctly. Key concept to remember, a logarithm is equal to an exponent value. So here we have the function y equals 2 to the power of x, and it's shown in this graph. And so this is our exponential growth function with a base of 2, what we call the parent function for our base 2 exponential family. And its inverse looks like this, and we'll talk about why it looks like this in a little bit. But this would be f of x, or y equals log base 2 of x. That's how we see this. Log or logarithm base 2 of x. So remember that these two would, since they are inverses, the relationship would be that all of the points for f of x equal to the x would switch to create the inverse f of x equals log base 2 of x. So this point here, which is 3, 8, for our logarithm would become 8, 3. So the exponent becomes the y value, and the power value of 8 becomes our x. So this would be log base 2 of 8 equals 3. That would be the idea, the reversing of that. For 2, 4, then it switches to 4, 2 in its inverse, the logarithm. For 1, 2, that switches to 2, 1. 0, 1 switches to 1, 0. This, remember, is negative 1, 1/2, so that switches to 1/2, negative 1. And then this is negative 2, 1/4, so this switches to 1/4, negative 2. So then graphing each of those points, 8, 3 is here, 4, 2 is here, 2, 1, 1, 0, 1/2, negative 1, and 1/4, negative 2. What also switches, if you recall, the horizontal asymptote for y equals 2 to the x, the exponential function, remember, is y equals 0, the x-axis. That y equals 0 also switches to become an asymptote of x equals 0 for the logarithm function, its inverse. Again, y becoming x becoming y. That switching of variables we've learned about. And x equals 0 is the y-axis. So it has an asymptote, a vertical asymptote, of x equals 0, the y-axis. And the curve looks like that. You might also recall that two inverse functions, the graphs of them are reflections of one another over the line y equals x. The line y equals x, the line of reflection, going through all of these points where x and y coordinates are the same. So the idea being that if we folded the graph along the green line, that y equals 2 to the x and the logarithm function here, y equals log base 2 of x, they would actually match each other once the graph was folded along y equals x, this green dashed line. All right, so here we're going to talk about that relationship on looking at this, why the inverse of 2 to the x was this log base 2 of x. So here we have our exponential form of, say, here it's written like with the power on the left. It could also be written as a equals b to the x. And here is our logarithmic form, which of course the sides could switch. So one of the things that we want to understand is, remember that for an exponential function or this exponential form, our base has to be a positive number and cannot be equal to 1. And the reason we exclude 1 is since 1 to any exponent is 1, we don't get exponential growth or exponential decay. We just get a horizontal line. A is what we refer to as the argument in a logarithm, and it is always a positive number. And there's no exclusions there. So it can also be a 1. It just has to be positive. So the base is positive but can't be 1. And the argument shown here and shown here, they have to be, or they would be positive values. So notice the connection, and I would encourage you to write these arrows and stuff and label in your notes. The positions of the base in our exponential form becomes a subscript in the logarithm. So it drops below the horizontal, notice. So it's what we call a subscript. That's where the base goes in the logarithmic form from its exponential form. The exponent, remember what I introduced as a key concept at the beginning on that first slide. Remember, logarithms are equal to exponents. So that's why we're equal to x, because the exponent is the x. Therefore, the logarithm is equal to x, because the logarithm is equal to an exponent. And that's a key thing. When we start doing some problems where we rewrite from one form to the other, we'll start by identifying the pieces and parts, such as the exponent and the base, and then we'll use the concept that logarithms are equal to the exponent to help us with the positioning. So the third thing, remember, is the argument, and this is a new term, and it's mostly used with logarithms. So the argument is our third piece, and that corresponds to what the power is equal to in the exponential form. So we'll just use the term argument for both of them for consistency. All right, so here we're going to look at some problems where our job is to complete this table by writing each given equation in its alternate form. So we'll be given either exponential or logarithmic form and have to rewrite it in its alternate form. So here we have exponential form, 4 to the third power equals 64. So what I recommend you do first is identify your exponent, which would be our 3, and then identify your base, which would be the 4. Remember what logarithms are equal to? Logarithms are always equal to the exponent. So we know we're going to be equal to 3. The symbolic notation for a logarithm looks like an abbreviation, but it's symbol notation, log. Remember that what follows the log in logarithmic form is the base, and the base must be a subscript, so it drops below the horizontal, like a line that we would be writing our log on, like, when we practice our writing in grade school and elementary school, it's like dropping below that line. And then the final piece, the 64, must be our argument, and it stays on the horizontal with the logarithm and the 3 and goes right there. So this is read log base 4 of 64 equals 3, which means in logarithmic form that 4 to the third power equals the 64. All right, so in this next example, we are given logarithmic form. So again, what we're going to do is identify the 3 parts. So what are logarithms equal to? Logarithms are equal to the exponent. So that makes the 1/4 our exponent. Remember that the subscript is your base. So in your exponent form, you have your base to your exponent. So we have 81 to the 1/4 power, and that equals our third part, which is our argument. So we have 81 to the 1/4 power equals 3. And you can see here that this makes sense. If you recall, 1/4 power means 4th root. So the 4th root of 81 means what times itself 4 times equals 81, and that is 3. All right, so now we're going to get into ones that involve some variables. So we do the same thing though. That procedure does not change. So our p is our exponent. The 2/3 would be our base. So what are logarithms equal to? Logarithms are equal to the exponent, so we know we're equal to p. Over here we start with our log notation. Then we follow with the subscript base, which is 2/3. And then on the horizontal, we have the third part, which is the q. So the q must be the argument. All right, now we have again logarithmic form. Now this one's a little bit different. You might notice that in all of our other problems, or in the problem here where we had our 81 was our subscript base, we don't have a subscript base here. This is what we refer to as a common logarithm. When we don't see the subscript base, it is always understood to be a base of 10. Always. That's what we call the common logarithm, a base 10 logarithm. So that tells us that our base is a 10, which we don't see written. What we're equal to, remember, is our exponent, because logarithms are always equal to our exponent, and that leaves the 10,000 to be the argument. So in an exponential form, the base is always to the exponent. So we have 10 to the 4th power equals the argument value, which is the power value of 10,000. All right, so now we have a negative exponent, and this purpose of this one is just to show that that doesn't matter. Exponents can be negative, remember. What can't be negative is bases and arguments, but exponents can be any real number. And so remember what logarithms are equal to? Logarithms are equal to the exponent, so we're equal to that -2. And then we have our subscript base, which is our 5, and then our argument of 1/25. You might sometimes see parentheses around a fractional argument. Just understand they're optional parentheses. The parentheses here around this 2/3 are not optional, because if we don't write the parentheses around the 2/3, then the p is only on the 2. So around a base, a fractional base, parentheses are required. Around a fractional argument, they are not required. All right, here we have our base of e, the irrational number e squared, one of the powers of e that we dealt with in our exponential functions. So we're going to talk about the base e logarithm a little bit now. So we start off with the same idea that logarithms are equal to the exponent, which is our 2. Technically, this is going to be approximate because we've rounded this decimal here. And then we have our logarithm. Our base subscript would be our e, and then our argument in the horizontal line would be our decimal 7.389. Now, log base e, this is what we refer to as the natural logarithm. And we're going to talk more about the natural logarithm in this unit and the next. But what we're going to introduce right now is the special notation we have for the natural logarithm. Remember how the common logarithm up here did not have this base of 10 shown? Well, the natural logarithm gets its own special notation, ln. So the whole thing, so we don't see the base of e, but we can differentiate between this one and the common logarithm by the fact that the common logarithm uses log and the natural logarithm, base e, uses ln, followed by the argument 7.389, which is about equal to the exponent of 2. So this is the proper way to write a base e logarithm. All right. So I encourage you to try these practice problems, pause the video and write them down, and then start again to check. All right. So hopefully here you have log base 2 of 1 over 32 equals -5. With typing with, you'll notice with the structure here, there's a parentheses around the 1/32. Those are optional. You'll notice too it sort of drops below the horizontal, and that's just because that's what the computer program makes it do. All right. On paper, I would just write it like that. All right, try this next one. Pause the video. Exponential form here for this one, you should have 9 to the 1/2 power equals 3. All right, next one. Let's take a look. This one, you should be equal to the x because the x is the exponent, and your base of 5/2 is your subscript. Parentheses are not required around a fractional base in its logarithmic form. They are required around the base in its exponential form. So those parentheses here are absolutely necessary. Here we usually don't see parentheses around bases at all. All right, so here we're going to, now that we've defined a logarithm, we've looked at the two forms, exponential and logarithmic form, we are going to use our understanding, our new knowledge, to help us to evaluate a logarithm. In other words, given a logarithmic expression, remember what logarithms are equal to? They're equal to exponents. So we're going to figure out what exponent a particular logarithm expression represents, and we're going to do this without a calculator. One of the things that we will use will be what we call the exponential property of equality. So we're going to use that because we're going to rewrite the logarithm in its exponential form, which is one of the skills we were just practicing. We will use a variable to represent the logarithm's value, which is the exponent. So remember, the variable that we're going to use to represent the logarithm's value is going to be then our exponent value, since logarithms are equal to the exponent. And then we'll use our exponential property of equality. So once we have our exponential form, we'll be able to create two powers that have the same base. And if the bases are the same, then we can conclude our exponents are the same. And we'll be able to solve for our variable that represents our exponent, that is our logarithm's value. All right, so let's apply that strategy. So here we are to evaluate each logarithm without a calculator. So I'm going to start with this one. So remember, this is a logarithm expression, and logarithms are equal to exponents. So it's that exponent that we're trying to find the value of. So we will start by using a variable to represent that exponent. Then we will rewrite this logarithmic form into its exponential form. So remember, our base is 4 to our exponent of x, then equals the argument value of 16. So now we use basically our number sense and our knowledge of powers to rewrite each of these as a power of the same base. Here we have a couple of options. 16 is a power of 4, so that's what I would do, but 4 and 16 are also powers of 2. So it would be okay to rewrite them as powers of 2 also. But it's a little simpler just to use the power of 4, since the first one already is a power of 4. So this would be 4 to the x, and 16 we know is 4 squared. So now, since the bases are both 4, we can conclude that the x must be equal to 2, which, remember, the x is the value of our logarithm, so our conclusion would be that log base 4 of 16 equals the exponent value of 2, like so. For the second one, again, it's a logarithm. It's equal to a value. Now, you can use x like I did here. It's not a bad idea, though, to sometimes use y, just because of the fact that logarithms are your exponents, and your exponents do become your y value in a logarithmic function. So you might want to get in that habit, too. Doesn't really matter what variable you use. You can use an n, you can use an a, you can use whatever you want to. It's just just a placeholder to help with the process of the math. So our exponential form then would be 5 here to the power of y equals 1 over 125. Now, you've hopefully recognized that 125 is a power 5, and that you know it's 5 to the 3rd power, and so that's good. But you have to realize that this structure does not allow us to conclude y equals 3, because one power of y is in the numerator and the other is in the denominator. So what we're going to do is use our negative exponent property to pull this power of 5 to the numerator. And remember that we normally use this to change a negative exponent to a positive, but if we pull a power from one position to the other that has a positive exponent, then it changes it to its opposite sign, which is negative. And that's really does what the negative exponent rule means. Negative means opposite of in that context. So here now we can conclude, since both we have a power of 5 equals a power of 5, that y variable equals negative 3, and that is then our exponent value. So our conclusion, remember, would then be that the logarithm of base 5 of 1 over 125 equals the exponent value of negative 3. All right, here's a practice problem. I encourage you to pause the video, try this problem, and then come back and check. Let's take a look. So here, used y, again, because it's a good variable to use to make the connection to the logarithm functions we're going to be talking about. And then we have 3 to the y equals 27. 27 is 3 cubed. Y equals 3. Therefore, the logarithm equals 3. Pause the video. Try this next one. Let's take a look at this next one. Here, hopefully, you came up with a value of negative 4 because you have to use that negative exponent property. When you pull this to the top, the positive 4 becomes a negative 4 exponent. So your variable value, here I used y again, is negative 4. And so our logarithm equals the exponent value of negative 4. All right, let's take a look at a couple of more together as examples. So the basic procedure, of course, is not going to change, but some of the differences in problems, we want to make sure everybody understands when something different happens, what that means mathematically or algebraically. So there are going to be some difference with these particular problems. All right, so this is our number 3, I believe. So again, I would start by letting this equal a value. I'm going to use that y. And so my exponential form will be 36 to the power of y must equal the argument of 6. So now 36 is a power of 6. It's 6 squared. And here's where things get a little different because that's on the side with my y. And so a couple of things going on here. We need to remember our exponent property that tells us how to combine the 2 and the y, which is multiplication. So if you need to write that down, it would be like a to the power of n to the power of m equals a to the n times m. And so this becomes 6 to the 2y power equals, and here's something that I see people often make a mistake. You remember, we're looking at the exponents here, and 6 is not your exponent. 6 is your base. 6 by itself has an exponent of 1. So you have to know that that exponent is 1 because in the next step, the exponential property of equality says if the bases are both 6, then 2y equals 1, not 6. And then our algebra, dividing both sides by 2, gives us a y value of 1/2 this time. So that is our exponent value, that 1/2. So log base 36 of 6 equals 1/2. And if you think about the number sense here, hopefully it makes sense, because 36 to the 1/2 power would mean the square root of 36, which is indeed the 6, which is our argument. In this fourth one, we have a fractional base. Again, I would start by letting my logarithm equal an exponent value, a variable to represent the exponent value, y, here. And so my 1/7, which is a fractional base now in exponential form, needs to be in parentheses to the exponent of y equals 49. So this time, I have to realize 49 is a power of 7, but 1/7 is also a power of 7. And so I actually have to rewrite both of them. 49 is 7 squared, and to make this one a power of 7, I have to pull this to the top, and it has an exponent of 1, so that negative exponent property makes that positive 1 become a negative 1. And then we have again the power property, which says that to combine the negative 1 and the y, we'd multiply, so that gives us 7 to the negative y, or negative 1y power, equals 7 squared. Now we can use the exponential property of equality, so base 7 equals base 7, then negative 1y equals 2. So y would be equal to negative 2. So negative 2 is our exponent value. So our conclusion would be log base 1/7 of 49 equals negative 2. All right. Third example in this group for us. So again, this would be, I think, number 5. So I'd let this equal a variable to represent the exponent value. And so my exponential form would be 4 to the power of y equals 32. Now this time, 32 is not a power of 4. 32 is a multiple of 4, but it's not a power of 4. So be careful about understanding your number sense, not getting those two things mixed up. 4 and 32 are both powers of 2. And this is where our number sense, being strong in our powers of 2, 3, 4, 5, 6, and so on, is very beneficial. So here I have to rewrite 4 as 2 squared. And I have to rewrite 32 and make sure I get this right. It's 2 to the 5th power. And if we're ever in doubt, do the basic math, okay, to double check your number sense. Multiplication, so I have 2 to the 2y power equals 2 to the 5th power. Therefore, exponential property of equality says 2y must equal 5. And a little bit of algebra tells me y equals 5/2, and that 5/2 then is my exponent value. So my conclusion is log base 4 of 32 equals the exponent value of 5/2. And again, number sense here should make sense. This means 4 to the 5/2 power, which is the square root of 4 to the 5th power, which is 2 to the 5th power, should equal 32. And 2 to the 5th power is 32. Here's a practice problem for you to try. Pause the video. Let's take a look at the result here. So hopefully you came up with 3/2 as your exponent value. Here you have to rewrite the 9 and the 27, both as powers of 3. 3 squared for 9, 3 cubed for 27. And then the 2y is your new exponent, and little division gives you 3/2. For the second one here, we're looking at having the 1/16, which is 16 is a power of 4, but you have to pull that to the top, which then changes the 2 to a negative 2. And 64 needs to be rewritten as 4 cubed. And then the 3y becomes our new exponent. 3y equals negative 2, so we get negative 2/3. All right. Now we're going to take a look at a slightly different problem here that still involves our understanding of logarithms. So we have this logarithmic function, f of x equals log base 1/2 of x. Find the following without a calculator. So we're going to find f of 4. Now remember, f of 4 means our x value is 4. So this would be equal to log base 1/2 of 4. This is a logarithmic expression, and this f of 4, which is our y value, remember, is our exponent. So it's really the same type of problem as we've been doing, just written in a function format. We're trying to find the value of this logarithm, which is our y value, which is our exponent. So this is why using the y variable in the previous problems helps draw that connection for us to these types of problems. So I have the y equals this log base 1/4 of 4. My exponential form would take my base of 1/4 to the exponent, which is my y, equals the argument of 4. 1/4 is 4 to the negative first power, which is 4 to the negative 1y. 4 to the first power there, so negative 1y equals 1. Therefore, y equals negative 1. So that's f of 4 in this case, because that's our y value, is f of 4. So our conclusion would be f of 4 equals negative 1, like so. For something like this one, so we have our f of 2 root 2 would be equal to log base 1/4 of our 2 root 2. This one is a little bit more involved. This is our y value, our exponent. And because we're dealing with our 2 root 2, we're going to have to change our forms a little bit. We'll talk about that. So I'm going to do my exponential form here first. So I have my base of 1/4 to my exponent, which is my variable y, equals my argument of 2 root 2. So here's where we can use our knowledge of, again, that roots and fractional exponents go together. So 2 root 2 is 2 to the first power times 2 to the 1/2 power. 2 to the first power, and root 2 is 2 to the 1/2 power. To combine these two root 2's together, we would add the exponents. 1 plus 1/2 is 1.5, which is 3/2. So this is 2 to the 3/2 power. This right here, our 4, is a power of 2. It's 2 squared. We'd have to pull that to the numerator using our negative exponent rule. So now I have 2 to the negative 2nd to the y power. And this becomes 2 to the negative 2y equals 2 now to the 3/2 power. Now I have a power of 2 equals a power of 2, so I can use my exponent, my proper exponential property of equality. So negative 2y equals that 3/2. Easiest way to work with a problem like this would be to use not division, but what division is equivalent to, which is multiplying by the reciprocal. So negative 2 times negative 1/2, its reciprocal is 1. So now I have y equals, multiply straight across for the fractions gives me negative 3/4. So in this case, the exponent value, what the logarithm is equal to, is negative 3/4. And that is also my f of 2 root 2 in this particular structure and context. All right, here is a practice problem to try. Let's take a look at the results here. So hopefully you came up with f of 343 equals 3. You might have had to do a little basic math. Hopefully you did not use a calculator. And so 343 is power of 7, and you can figure out that's the only thing it could be here because 7's a prime number. So the only way that we can do this problem this way is if 343 is a power of 7, and it's 7 cubed. That makes our y value equal to 3, and then our structure of our conclusion, since what we're finding is f of 343, would be that way right there. All right, that does end this lesson. I hope you have a lovely day.